We're going to be listening to Lucas and Carlos from IOActive, compromising industrial facilities from 40 miles away. So thanks, you guys.
Thank you, Chris. Good afternoon, everyone. Thank you for coming to our talk. Today we are going to talk about how it's possible for an attacker to compromise industrial facilities from 40 miles away. We are both security consultants and researchers at IOActive. We are from South America, and our main interests are those that you are seeing now. So the agenda for today is to explain you the motivations behind this research, the industries and applications that the vulnerabilities that we found affect, and the wireless standards that are used by the vendors that we are going to show you. We are going to show three of the most important vendors out there of industrial wireless devices, and we will show how we found and the methodology used to find these vulnerabilities.
As a motivation for our research, we have several reasons. One of them is the lately years attacks on critical infrastructure and the impact that has been created by these attacks. As we all know, most of them has been due to the misconfiguration or the direct connection of industrial controls facing the internet. No? The other one is the insider threat. You know, the guy that works in the facility and uses a USB and plug it in a control room to launch a malware or to launch a zero-day attack and compromise the whole device in the facility. So we were thinking about what else you can accomplish, or what new attack vector you can find to compromise these facilities. So we found that in those industries, the use of copper, the use of cabling, all that things are really expensive, especially in hazardous places. No? So there is a solution called wireless, industrial wireless solutions. This helps to reduce the cost of the installation and minimize the risk of the workers at the oil field that has to go to a hazardous place and make measurements on something. It also allows us a new way to control and modify these facilities. The application of these wireless devices are mostly on oil, gas, and refinery petrochemicals. You know, like these devices, these transmitters, as you can see, one of them here. For example, this one is being used to monitor the temperature in an industrial process. Another application is in energy. You have, for example, capacitor bank controlling, power outage reporting, all this done wirelessly. But with all these solutions also comes some challenges. For example, defeating electromagnetic interference in an industrial facility. It also you have to handle the attenuation and reflections on this application, these wireless sensors. Also, this wireless is different from the business wireless like Wi-Fi. This is totally different.
That's because mainly reliability is more important than speed. So these protocols are more lightweight.
So in this wireless sensor network, we have to use what we call cryptographic key distribution for the secure communication between all the devices in the facility. So there's a lot of limitation on them. For example, the amount of devices and how you're going to share this secret between them. The more you have, the more it will be difficult to share a secret. But it also comes a solution like out of band, in band, and factory preloaded. In this case, we use out of band, which is plugging a cable in the device and installing the secret key that will be used for the secure communication between all of them.
Okay, the first standard that we are going to review is the IEEE 802.15.4. This is widely used on industrial devices, and this is mainly because it's focused on low power and low speed devices, and also allows you to set different security features and set, for example, an algorithm and an AES key. But this standard only defines the lower layers of a protocol. So the maintenance of that keys is not the main responsibility of these layers. So the upper layers that will use this protocol will have to maintain these keys and to revoke them and all that. So for example, Zigbee, Wireless HART are some common protocols that uses this standard on the fundamental lower network layers. So for example, we're going to review Zigbee very fast, but this Zigbee is not particularly very used on wireless environments, but this introduced a new concept for the keys, that is a trust center, which is a node that will store the keys for all the network and will authenticate every device. And this trust center has the ability to change the key, the previous key that all the nodes are sharing, with a new one, but it's just one key for the entire network. This is on the standard security mode. So they came up with another scheme that is more complex, because if you compromise one of these nodes, you will end up having the network key, which will allow you to communicate with all the nodes on the network. So there's a high security mode in Zigbee that they incremented the amount of keys required. Each one of these keys will have a different is with different purpose, because each key, for example, one key is for unicast communication, one key is for multicast communication, and like that. For example, that a new node is added into the network, a new node B, and the trust center must set a master key, which will secure the other keys that will be used for other type of communications. And this key is very important to have them transmitted over a secure transport, because some implementations might let you update this key wirelessly without any kind of encryption, because the master key is the most important one. So they recommend to use always out-of-band techniques, which is connecting a serial cable and sharing the secret in that way. So the link key is for unicast, and the network key is more a multicast approach. So on the other hand, supposing that one wireless device manufacturer uses a radio model from another vendor, it happens that there are many schemes possible for distributing the keys or for storing the keys. So for example, we have 3 entities that I'm going to review very fast, but we have on the paper a more detailed explanation on each of them. But for example, the radio models, you can pay for an additional fee, and they will set you a special device ID that will let that all the devices all the radio models that are bought from the same on the same company will let you communicate just with the same devices that has the same key in the firmware. This is widely used, but it's expensive because it's $1,000, for example, and the device manufacturers maybe don't want to buy one for each of their customers. So they tend to set an encryption key when this device is already assembled. So the device manufacturers have 3 choices, and they can, for example, set a per client encryption key that they will track every of their customers, and they know that that customer will have a special key, and all the devices that will be brought to them will have that key. Another way is that that this company that sells this kind of devices uses just one key for all their customers, and we will see which is not a good idea to do this. And the end user has different choices that they can do. For example, in Orange, they might void the warranty of the device, because if the software that this device doesn't allow you to set or change the radio encryption key, you will have to remove it, and you possibly void the warranty. So it's very common that these devices have a device company encryption key. So all the devices and other companies that bought the same device will have the same key. And the problem with that is that there are shared secrets among different companies. And the main problem is that an attacker can buy the same device, which will end up buying the same key, will remove the radio model from that, and he doesn't even know to know the secret, because the secret will be stored there. It's not necessary to read it. You can interact with an API with a radio model, and then you can send frames to the air using the encrypted message.
Now we start the fun part. The first vendor that we're going to analyze is a well-known vendor. Probably many of you can recognize the photo. It's well known in the industry, and it allows you to have a point-to-point antenna connection between the two devices, and it's reachable by 30 miles. This device comes with a software in order for you to install and create a new network, a new wireless network. This software comes with a user guide, and the user guide states default values built into the software work well for initial installation. So, as you can see there's a passphrase generated that it will be used to generate the AES key for the secure communication. So we were intrigued on how they are creating this key that will be used for the security of the devices. So we reverse engineered the function that was handled that, and we found a really nasty, unsecure way to do it. They use the time of the local machine to generate the key that will be used for the secret communication between all the devices in the field. They use the run function, which all we know is a bad ANSI function, so it's really bad the way that they create this, and this offers a low entropy.
So by using a low entropy seed, we could replicate the same algorithm on another machine, because on Windows, the srun function and the pseudo-random numbers are the same across the different versions. So by having the seed, we will iterate over all the possible seeds that this device could have, that will be from the instant that we are now to the past. So we are going to, for each second that passes to the past, we are going to calculate which is the passphrase that corresponds to that time. So as you can see there, we executed that binary that we did, and we can grab a passphrase. So we were trying how bigger is the scope, because we don't know if this device was configured 10 years ago, 20 years ago, but no. We found on the help file of this vendor that we found the passphrase there. So we started to look, okay, when was it generated? And it was on 2008. So our scope of possible passphrase will be that one.
So let's say you want to attack the devices of the vendor without having found the vulnerability that we explained it before. You need to brute force 25 to the power of 70 passphrases, which is almost impossible in a specific amount of time. But with the peak PRNG attack that we found, you only need to generate 156 million passphrases, which only took us a couple of seconds to generate that. This is easily breakable by an outsider, and with this vulnerability, an outsider can fake the devices on the field, can fake the data that they are sending. And what we recommend to the vendors is that when they try to generate this kind of function to make secure keys, they need to check them for further. They need further research with all this, and they need deep testing. The second vendor that we're going to show you is the most well-known and most used in the industry. It's self-proclaimed market leadership in oil and gas. It offers a different set of family of devices, which are the wireless gateway, which is this one that we have here. This one. And the wireless transmitter that we have here.
This one.
As an example, this is how they they're being used, the topology that you can have with these devices. So as you can see, there are different families: the compression monitoring, the tank monitoring. There are a lot. The most important one is the gateway, which made the name of our talk. It offers a maximum length of 40 miles.
Yes.
As you can see, these are photos that we found, and we managed to identify that they're actually using these devices in a specific fields. All right. The way they are being deployed is as follows. It's a set of transmitters, like this one, and they are connected to a specific gateway. Those gateways are receiving the data from the transmitter and sending it to, let's say, a PLC, RTU. It all depends on exactly what they're using these devices for.
Okay, we started to think how the devices access the wireless information securely with this scheme, with this vendor. So we found the concept of an enhanced site security key, and the vendor states that this is designed to provide an additional level of protection for RF packets. And they also said that this feature is not available on some older versions of legacy devices. But it's interesting because these legacy devices can also communicate with these new sensors. If you have the new version of the sensors, you can also communicate with the older ones. So we started to think if this security key is an encryption key, because this key is generated and distributed using a serial cable with the tool that the vendor provides you. So when you create a project file that you will set the specific configuration for each of the devices that you are going to interconnect, you set the interval of time that you want, for example, that the transmitter to send the information, because these kind of transmitters have a battery that, for example, that lasts for 10 years, and if you higher the amount of time of the interval, you will get more and more time available. So on the documentation, we found that they said that the project file, every time the project file is changed, the file name, a new site security key will be assigned. So we start thinking, okay, this could be a per site encryption. Every different site that will be created on the engineer's machine will have a different key, and this allows you to have different layers on the same physical location, so they don't collide. So this key must be somewhere on the project file. So we reverse engineer the function that we start looking, okay, when the file is going to change, you're going to verify that the file name changed. So we found the following disassembly. This basic block just then calls again to the time function to calculate a value, and it returns the seconds elapsed from 1970. So this is a number that is just 4 bytes, and it updates the security key with this value. So we grabbed 2 different projects that were created identically, but with different file name. So the key must have changed. So we compared them both, and we identified that it changed exactly, and it was the site security key that was changing. So,
okay. Before doing more research on the devices, we needed to get more information about them. So, in the webpage of the vendor, we found that we could download a firmware. We could get an idea of the architecture and the processor that they're using. So, by downloading a firmware, we found that it was an incomplete firmware, which is just an update, and it only has compiler string, so it was really hard to see what we could do with it. But we did a Google search, and it turns out that these compiled strings were from a IDE for a specific processor, which is MSP4030. And also, we found on some videos and some tutorials that the vendor has on their webpage for installation and deployment, we did a zoom on this image, and we found the exact model of the processor that they were using. As you can see here, we also identify in a YouTube video of the vendor, we also identify the specific radio that they were using.
So what we knew at that time is that they were using a site encryption key that is weak because it's just 4 bytes. So we wanted to know if there is another key that could make us very difficult to attack, because if we bought the devices and this per client key was set, we couldn't exploit the weak site encryption key because there will be another level of protection. So we sent an email to one of the reseller sales engineer, and we asked what happened if we borrow a device from another customer. Will it connect with our family of devices or not? So they told us that just we need to upgrade the configuration files. So the only limitation on this is that the site security key will be there and no other kind of keys are there. But we don't know at this time if they have a device company key that will prevent us that using a transceiver to read those packets, because maybe it is encrypted with another key from the vendor that we don't know. So we start looking at the firmware images we had at that time, and we had two kind of different architectures and two kind of different disassemblies. So with these two different kind of images, we start looking at possible hard-coded keys on these firmwares. This is possible because the disassemblies are different. So we start grabbing 4 bytes from one of the firmware images and start looking at the other firmware. So we found that bytes on the right image that were in common, but it finally ended up that was just a CRC calculation. So we were nearly close to find an encryption function because there are some source with it using that table, and that table that you see there is across all the versions of the firmwares of that family of devices. So we said, okay, let's acquire the devices and check if this is possible, if we can break this weak site security key. So we bought an RTD temperature transmitter that I showed you some minutes later, and this uses a platinum sensor to collect the physical values of the environment, and it will send using a transmitter to the gateway, and that one is the one that collects all the information from all the transmitters and will be connected to an HMI or a PLC. So what happens when one of these nodes, for example, if this node gets stolen at my facility, what happens with that? So we found that by sniffing the communication between the tool that is provided by the vendor and this device, we found that there were some sequences of bytes that if we managed to send it through a serial cable, we could extract the site security key from the device with no protection of password so it's not encrypted really on the device itself. And we could also extract the entire project file without problem. So an attacker could know which is the topology that these devices have. So we started to think, okay, let's start with the cryptographic attack behind this. We already bought the devices. We bought a transceiver. So we started looking at the protocol that these devices send. Every 10 seconds, we program the interval from the transmitter to 10 seconds. So we start looking, okay, every 10 seconds, we will see nearly the same packet. So we knew that was the one where we are looking for. So we developed a tool to send and receive 802.15.4 data because one of the previous images showed us that they were using this protocol because we already identified the radio model that was using, and it only supports that protocol. So the vendor used their own layers built on the top part of that protocol. So we were going to break this site encryption key, and we found out that the key was not really used for that encryption. It was live from the vendor because there is no protection at all for RF packets, like they say on the vendor's guide. And maybe it's that because maybe they didn't explain a little more about this protection because they were going to mess it up more. So okay.
So we developed a demo to prove this. We're using a HMI project, and we're using a video from the Chemical Safety Board as a background. It's just a simulation, but actually the data that you will see here on the right side is a thermometer. It will be measuring the temperature in this room, and what we're going to do is that we're going to send fake measurement to this gateway, pretending that we are the temperature, and we're going to bring it down into a level in such a way that it will think that it's physically getting cold, but in the real life it's getting really hot until it explodes.
Ahí está.
Okay, so as you can see, the temperature there in the red line is the temperature in this room. So I'm going to rise it with my body heat. See?
No, too big.
Let's wait. What is it? You see? 71. It's getting warmer and warmer. And now what we're going to do for the demo is that we're going to bring it down.
Okay, first, what we are going to do is to start sniffing on the air to receive some packets. And what we are going to do is to use the security key that we read over the air to authenticate our future messages. So it's as simple as that. So there a wireless gateway is detected.
So he detected the wireless gateway.
And we map the wireless information that is out there, and we know that this sensor has those readings, and what we are going to do now is to inject in the wireless gateway, that is the one that collects the information. We are going to inject fake measurements. Yes. Okay, we are going to turn on the pump. Sorry. Too difficult to do it in the same machine. No, the other side. What is? Pon acá la otra. Sí, se aparece. Aquí debajo. Ahí está. Genial. Ahí está. Okay. Okay, so we are going to set a minimum level for tampering the sensor, the temperature that is going to reduce. We are going to do it slowly to just show, we can do it instantaneously, the reading, to change the reading on the device, but we are going to do it very slow, so the system will think that the temperature is really going down. So we are going to minus 10, and we just need to calculate the sequence number of the next 802.15.4 packet, use the site security key for authenticating, and then we can see that the temperature is going down. So when a level is hit.
So we show in the thermometer that the temperature is going down, getting colder, but actually on the physical one is getting really hot. As you can see. You see it's getting hotter?
Yeah. That's because the process tends to hide the temperature, so it can stabilize the reading. So it starts warming up
until it explodes. So if this happens to you, just keep calm and get to the chopper. Oh, sorry. So if this happens to you, just keep calm and get to the chopper. The other bug that we found on these devices is actually a remote memory corruption, not in the sensor, on the gateway. So we recorded a live demo due to the criticality of this bug. We don't want it to be, we don't want it to be leaked. What we can do with this is actually stop all the gateways from receiving data from the transmitters. All the gateways at the same time. So we call it Plan Killer, and we recorded a video that we're going to show you right now.
This was possible mainly because we could identify all the fields on the protocol, because we already have a way to communicate with these devices. So we are going to show, no, we better reduce it a little bit. We are going to show you the output of the debug interface when connected to the wireless gateway. So we are going to view when a packet is received by the gateway, it will print a message. And if it doesn't receive any kind of information over the air, it prints an RF timeout, because all the devices are configured to, after 1 minute of not receiving any data, to print a timeout. So what we do now is to execute the same tool. We map all the devices that are at the air, and we just calculate which is the next sequence again the 802.15.4 packet, and we send the malicious packet to the air with the transceiver. It took a little bit because the wireless gateway stops receiving data, but after a minute it will print the message, but it's already disabled.
And just keep in mind that these devices are being deployed in hazardous places, so it will be really hard for them to troubleshoot something like this. They actually have to go and to have physical access to the devices and restart them. You see a timeout there?
Yes, a timeout means that he's not able to read the wireless information. So the only possibility is, like he said, to reboot them manually.
Exactly.
Okay.
So if this happens to you, this is how your facility will look like.
Okay, the profile of the third vendor that we are going to review today is a very known vendor in sensors. They claim that they are the undisputed leaders in sensor. The topology of the devices that they provide is nearly the same as the other ones that we already saw. There is a wireless gateway that collects information and the transmitters that sends it to the gateway. So possible topologies of this and applications are, for example, in oil and gas facilities, and there are different kind of possible interconnection between them, point-to-point, multi-point. So they are mainly used on water and treatment plants and all kind of stuff that involves reading physical values. So we base our research this time by reading at the technical note of this wireless family. We found that they claim that there is a multi-layer security protocol that protects your data. So we said, okay, what's this multi-layer security protocol? So we start reading at this technical note, which is just 2 pages, and they outline the network security, data security, and data integrity. We already reviewed this statement that we are going to view now on the paper, and there is a more detailed explanation of every code that they make, but it's a very funny reading. You will see now why. So they also said that the security of their devices is far exceeding most of the wireless systems in the market today. So, for example, one quote that we found there is that they say that this family is designed to completely eliminate all internet protocol-based security threats. And Wi-Fi access points have the potential to route any and all data packets, which is why these systems use encryption. Evidently, these guys doesn't know why it's used encryption, because they also tend to think that using Wi-Fi or potentially routing packets will compromise the facility, but there are another ways to manipulate the information that is sent to the air. So it's a very funny slide. So another quote is that they say that this protocol only carries sensor data values and only I/O data is transmitted on the wireless layer. They said this multiple times, like only carries, the word only states that they despise this kind of information over the air, and it looks like they maybe hired someone to write this technical note to say good things about their design, but it's very weird.
They say that Wi-Fi has serious issues, but they also claim that proprietary systems are more difficult to have than open standards, which is really wrong.
This is one of the most important company in sensors.
Yes,
So-
exactly. They also say that they offer frequency hopping, and we all know that that doesn't mean that it's secure. They also claim that there's no way to transfer a malicious executable file. Of course, there's no way because they're sending data, they're sending temperature, we're not sending a Word document or something like that. The protocol doesn't operate like an open protocol such as Wi-Fi, so it's not subject to risk of an open protocol. This is the most, it talks by itself.
So the conclusions of this research is to always review how the keys are generated and distributed. It's really important to use always, if possible, out-of-band methods, which is sharing secrets using serial communications and not using in-band methods, which is sending it through the air. To, for example, the first time you buy the devices, they say that, okay, there is a feature that will allow you to configure the devices very fast and wirelessly. So this might be wrong because the secret will be eavesdropped on the air. So another thing is that the 802.15 protocol offers security at one of its layers. So most vendors doesn't know that they can also enable that one to have a cryptographic key at different levels of the protocol.
As a conclusion, we found that these devices don't use any physical anti-tampering, which means that if I steal one of those devices, I can retrieve the key. We also suggest that they do audit source on the software that is being deployed on the gateway or on the sensors. And we also suggest the use of ICS cert hardening dyes for better, more secure applications.
Okay, we all know that this problem with the complexity of distributing keys on wireless sensor networks has been an open topic for a while, but we know that this journey of keys allows practical attacks among them. So it's time to start thinking about which are the devices that are on our facilities and to come to the security industry and to watch for standards that are really growing up in their maturity because they are incrementing the amount of keys that these protocols can have. For example, for different kind of communications, they use different keys. So that's a good approach to have different layers.
Also, that even that there is some good practices in the industry to implement cryptographic communications, they also can fail at implementing them. As we saw, they use AES, but they don't implement correctly the entropy for the key. There's no evidence of previously secure reviews on these devices, and it's really cheap for somebody to go to a site and test for these flaws. And you can get the hardware and the software is open source.
Okay, we would like to thank the ICS CERT. We disclosed the vulnerabilities with them some months ago. And also the references that we read a lot of papers from that people that has contributed very well to the wireless security industry. So also we would like to thank IOActive and our friends and families.
Thank you.
Thank you so much.
Thank you very much.